maybe not too complicated, but you have to look at it in in careful detail. And what I have in here is I have Java code, right? To just illustrate what can you do with a graph. So first of all, a graph is yet another type of a tree. In fact, trees are a type of graph. Okay, a heap is also a type of graph. So a tree is a type of graph. A heap is a type of graph. And a graph can have multiple connections, right? You don't have to have like a unique path from one place to another place, right? And one of the very common things that you are going to be asked to do in job interviews actually is, write an algorithm or write pseudocode, or maybe even write a code so that you implement the depth first search algorithm or breadth first search algorithm. If you go look at that link that I gave you with the scholarships, you will find that those questions pop up in there. All right. So first of all, let me tell you what a depth first search is. So for depth first search means this is the root of my tree, right, at the A, and we're going to try to get as far away from A, get all the way to the end before we get to the next node that is closer to it. So in other words, imagine you're in some kind of a maze, right? You're trying to find your way out, and you have a piece of string or a ball of string with you, right? You tie it, and you tie it where you start, and you go to like the first intersection. And at the first intersection, there's multiple ways you can go to, right? You tie your string to that intersection, and you start exploring one of those possible ways out, right? In every intersection, you tie that string to that intersection, and you take your next turn until you dead end, right? And when you dead end, you pull your way back to the intersection where you started from, and now go to the other way. Mark this one with like a little stone or something that you visited it, and then you go to the other path. And if you dead end there too, then you go back, you mark both of them as visited, and then you follow your way back to the next intersection. And that is basically what a depth first search is. And that kind of an algorithm is actually used in games, right? So in some kind of a game where you can make a choice, and then based on that choice there's a bunch of consequences, right? That is where this thing would come into play, those kind of decisions. Okay. So how do we do these connections? Well, the connections are done basically with a two-dimensional array. Okay, so if you look at this table that I have underneath it here, right? It's basically like an Excel spreadsheet, right? And by the way, this whole point, the reason I started talking about this is to show you that this is how I do it, right? You get the code, break it down into little pieces, and try to visualize how it's working. And if you don't do that, you do not have a complete understanding of these things. Okay? So anyway, what we have in here is we have this is my graph, right? So A is connected to B, A is connected to C, A is connected to D, and A is connected to E, right? So what we're going to do is we're going to write a spreadsheet, and all the rows are going to be labeled as A through I, and all my columns are also going to be labeled A through I, right? And then whenever there's an actual, let's say for example A is connected with B, we're going to put a 1. Right? A is also connected with C, so on row 1, right? On row 1, we're saying that A is connected with B, C, D, and E, right? And the zeros indicate that A is not connected to F, G, A, H, and I, right? And we do the same thing with the column of A, right? Column A, we put a 0 when there's an A and an A, but the other ones, B, C, D, and E, are 1s, right? And then the other ones are zeros because there's no, they don't meet, right? They're not connected. Okay, so now based on this connection, based on this matrix, is how we're going to implement our breadth first search algorithm. And by the way, there is a tree implementation. This is the array implementation. Okay, so the idea is this. What we're going to do is we're going to try to let me walk you through it. Okay, so the first thing what you're going to do is there's a function in there, Java calls it methods, which is going to return the unvisited vertex. Okay, so let me see how I can explain this to you. All right, so first of all, what I'm going to do for this is I'm going to start with like a little bit simpler little bit simpler thing, right? So this is my, first of all, let's build a matrix, right? I guess that's where I should start. Where did I build this matrix? Right here. Okay, so in here is where I'm going to build my matrix, right? So this here is, call this the main, right? This is the main. We're going to make a new graph, and we're going to add these different vertices, A, B, C, D, and E, right? And then we're going to connect these edges, right? And again, this is the picture of A, B, C, and D, and E, right? And this is the connection that we're going to try to make. So the connections are basically A and B are connected, right? That's what this is. How we're going to establish this connection? We're going to have a function called addEdge, right? Which allows me to connect vertices with two sets of indexes, right? So in here, what I'm going to do is I'm going to call addEdge01, right? And then when I do that, that's actually in the main right here. So if I do addEdge01, then I'm telling it, okay, the ADJ matrix 01 is equal to 1, and then the ADJ matrix 10 is equal to 1, right? So this is my matrix. So if I'm basically telling it this is equal to 1, which is this piece right here, and then I'm telling it this is equal to 1, which is this piece right here, right? Yeah, this is a two-dimensional array. This is the adjacency matrix is just a two-dimensional array, and it looks exactly like this, right? It's basically storing these numbers, okay? And then I do that for the other ones. So let's say, all right, so then the node or vertex B, right? I'm going to do connections 1 and 2, right? So this is the 1, right? And this is the 2, okay? So I'm telling it, okay, do this 1 and 2. So adjacency matrix 1, 2, which is this one, right? And I wrote the numbers, right? This is the 1 and this is the 2, right? Those are the indexes of this one, right? And then I go to the next one, then 2, 1 is equal to 1, right? Row 2 is this one, column 1 is this one, so now I'm changing this one here. So that's why there's different colors, right? And similarly, we basically fill up all these different ones in here with 1s and 0s, or just basically just ones to indicate what's adjacent to what. In other words, so that we can create this relationship in our program, right? This is the idea that we're trying to model. Okay, so now that we have created this adjacency matrix, also in here I am creating an array of vertices. Okay, so we're gonna have like some kind of this is my graph. It has like an integer array of, or an array of vertices, okay? And what is the vertex is basically something that just has a label, a character in it, okay? The important thing is, so think of it as just a letter, right? Each vertex is just a letter buried inside of a class, okay? So anyway, I have a vertex list in here, and every time I insert a new vertex, I'm increasing the number of vertices by 1, right? So basically what I'm doing is I'm creating this, right? You see how much easier it becomes if you just really break it down into little details. So, well, that's you got to start somewhere. Yeah, you can do it on paper first, and then if you get tired of doing it on paper, then transition to Excel. But the point is you have to be able to just like keep unfolding this code until it's like completely demystified in front of your eyes. There shouldn't be any doubt. Okay, and then. Anyway, so that's what we're doing here. We're creating an array of vertices, right? So, and then we created the matrix. Okay, so that's it. One stores the letters, the other one stores the relationships between these different letters. Okay, so now we're going to implement the breadth first search algorithm, or the depth first search algorithm. Okay, and what is the depth first search algorithm? Well, it's this piece of code right here, right? And the rules for the depth first search algorithm are these. If possible, visit an adjacent unvisited vertex. Oh, by the way, each vertex has a letter and it has a marker whether it was visited or not, just like what we were talking about in the maze, right? And if it's unvisited, you mark it and you push it on a stack. And surprise, surprise, we're going to use a stack. And guess what stack? The same exact stack we wrote, right? You can use that same exact stack, no modification, to create this data structure. Okay, and now if you can't follow rule 1, then if possible, pop a vertex off the stack, and if you can't follow rule 1, basically you're done. Right? And if you look at these, you're like, okay, that kind of makes sense. The maze and these 3 rules make sense, but really break it down into little pieces of code. So this is the code. All right? So first of all, this is the depth first search algorithm. Okay? And yeah, we're going to be pushing things on the stack. We're going to be popping things off the stack, plus a little bit extra in there so that we can, make it, work the way we want. And again, this is one implementation which does not require recursion. So to me, this is actually a little bit easier to understand. Okay, so might be a little bit longer. It might seem like a little more code, but it is easier to understand. That's what I think, at least. So anyway, so in here, what we have is we have a vertex list 0 dot visited is equal to true. So what are we doing? We're getting, remember the vertex list? Where's my vertex list? Right here. So this is my vertex list, right? So each of these, other than a letter, right, it also has true or false. So what we're saying is, we're telling it that this thing here now is visited, it's true, and all these other ones here, false. All right, so the rest of them false, they haven't been visited. Right, so in other words, we're at the A. Right, so we visited the A. Okay, yeah, it basically tells the vertex, okay, you've been visited. So since the vertex has a character for the letter and true was visited variable for true false, right? So that one's true. We visited it. Okay. What we're going to do is then we're going to display the vertex, and the display vertex is just show the label of that thing, right? And there you go. That's the letter A. Okay. The next piece is now push it on the stack. What stack? Well, imagine some kind of a stack. Right? And what are we pushing? We're pushing 0, right? We're actually pushing the indexes of this array. Okay? So I pushed the 0 index in there, which means that's the letter A, right? It's just the index, right? The stack only holds the value 0, but I'm just putting the A there so we can remember what it is. Okay? And then we go to the loop. Now there's the loop in there, and this is where the real depth first search algorithm is, right? So we're going to go and we're going to tell it, keep going on while the stack is not empty, right? So the stack is not empty. The stack is not empty initially, right? We put the thing in it. So now we're going to go in there and get into the loop, and I think that is, where do I start this? Starts here, right? Okay, so first, and again, this is what works for me. I guess because I have a degree in engineering and I messed around with Excel a whole lot, I'm comfortable with Excel. I don't know if any other software will do a better job than Excel for this, though. Maybe, but for me it works great. Anyway, so I have my stack, right? And what we're going to do is stack peak. And what is the stack peak going to return? Well, the stack itself, remember the stack stores the indexes of the vertex list. Okay? So in other words, when I say stack peak, it shows me 0. This is the thing that's stored in it. If I had 123 stored in it, stack peak would show me 123. Okay, but it just shows me, yeah, peak always shows, remember, from stacks, you have peak, you have pop, and push. That's it. Right? Peak shows you the thing on top of the stack. Okay, so the stack peak returns a value of 0. Okay, so I have v get adj unvisited vertex 0, right? That's this piece here. Okay, well, where does that go? All right, let's trace it. So I'm going to this function in here, right, called get adjacent unvisited vertex, right? And I'm sending over an int v value of 0, right? V is 0. And that's why I go in there and I recreate my little table in here, right? This is what I had from before, right? And what I'm going to do is, here's my loop in here, right? So I have J is going to be these values, the values of these indexes, okay? And V is fixed at 0. So what I'm telling it is, this loop is going to go through this row of cells right here, okay? And then what is it going to do? It's going to look for if the thing is 1, so it's going to try to find a 1 that hasn't been visited, right? So if the vertex, each of these are vertices, right? So each of these, so it's going to go through the adjacency matrix, which is this, right? And it's also going to look at, where's the other one that I had? It's under somewhere. Where did I put it? There. It's also going to look at if the vertex itself was visited or not, right? So the only one that was visited so far was this one, right? That one has been visited, right? So, and we're looking at this row here. So what is it going to do? It's going to stop at the first one that has a 1 and hasn't been visited. Well, none of them have been visited yet. So it will look at this one. Is this one a 1? No. Then it will go to the next one, right? Is this one a 1? Yes, it is. Has it not been visited? No, it hasn't been visited. Perfect. Then it's going to return the J. What's the J? The J is the value for this cell, right? So J is 1. So what does it do? Returns the 1. Now this thing is equal to 1. Well, let's go back where we came from, right? And is V equal to 1? No, I mean minus 1. No, it isn't. So we're not going to go into the if. We're going to go into the else. What does the else do? Well, first thing it does is it marks V1 as visited. So now we marked the B as visited, right? So now the B has been visited, and we're going to show it. Display vertex shows you the B. So we showed the A. First we showed the A, then we're showing the B now, right? And then the next thing we're going to do is we're going to push the V on stack. What was the V? The 1. So we're going to push the 1 on top of the stack. So now this is my stack. Okay? Now we go back and we're going to resume. We're going to do this loop again. Right? I go down, I copy paste this all this crap from the top, right? And then I go, all right, so now does stack peak, right? What do I peak? When I peak on the stack, I'm going to get a 1, right? That's what's stored on the top of the stack. Okay? So this thing returns me a 1, right? That means that I'm going to call get ADJ unvisited vertex with a 1, right? I go to this, now I go to this function here, V is a 1, so that means that I'm going to be looking at this row, right? The V is now equal to 1, okay? So J still starts from 0 and it goes all the way until the end. So we're going to start here, right? And we're going to keep looking if any of these have been, first of all, is this equal to 1? Well, according to the adjacency matrix, yes it is. Now let's look at the second piece. Vertex list J dot visited, is it false? Well, vertex list 0, we marked it as a visited. So that one doesn't count. In other words, this doesn't count because we already visited it, right? We marked vertex list, sorry. The 0 is actually the A, right? This one is the 1, right? 0. No, this is the A, my bad. Yeah, so we're comparing the B to all the other ones, right? So we're checking to see if A is visited, it is visited. If B is visited, it is visited. The one that hasn't been visited yet is this one, the C, right? So in the adjacency matrix, we have a 1 and the vertex list J, right? So when J is equal to 2, right? Vertex list 2 hasn't been visited yet. So now what we're going to do is we're going to return the 2, return J, right? So we're getting the J, we're returning it back. Now V is equal to this thing, right? Is it equal to 1? No, V is not equal to 1. So we're going to go to the else. We're going to mark this thing now as a true. So now we get to this case. Now it's true. And we're going to push it on the stack. We're going to show it. We're going to show the C. We're going to push it on the stack. So now we push the index of the C on top of my stack, right? That's what the stack looks like. Now the next step is, we're going to keep doing this, but good news is now we're all the way at the end, right? We already looked at we already showed the C. Show the A, the B, the C. We're at the end of the, we're dead-ended. Okay, so let's see what happens now. I go in there, and I have this one more time. So this time I am at C, right? So when I do the stack peak at the bottom, right? The peak is going to return a 2 for me, right? So that means that I'm calling this function now with a 2, right? So now V is equal to 2. That means that we're at this row right here, right? This is the V2, right? We're at this row. Okay, we're still going to go through all of them, but since all of these are already visited, right? The 0, the 1, the 2 are visited. That means that we're basically only going to look at the last one. And is that one equal to 1? No. So at that point, we couldn't find anything. That means now we're going to return a -1. We get the -1, we bring it back. V is equal to -1. All right. Now V is equal to -1. We're going to do a pop, right? The stack pop. So the stack changes from this here before to this here after. Okay. So we pop the little thing off the stack. All right. Now we're going to go back to the loop. We're going to do the same thing again. This time we're going to look at the B. Right? And since we already examined the B all the way, but let's look at it. So first of all, the peak, right? Peak gives me a 1, right? We put the 1 into this function, right? So V is equal to 1. That means we're looking at this row here, right? And all of these are visited, right? The first 3 things are visited. The last one, the last one isn't visited, but it's not equal to 1. So we couldn't find another one. That means now we're going to return a -1. We're returning the -1, right? So V is equal to -1. If V is equal to -1, we pop that thing off the stack now. So this is what's left of my stack. I only have a 0 at the top, which is okay. Now we're going to we're going to do another peek, get the A, right? The index of the A. I think I messed up. Yeah, it's not a pop. This time it's a push. All right, there you go. So what are we going to do? We're going to do V of 0, right? I mean, sorry, get the stack peak returns a 0. We get this 0. We feed it into this function, right? Again, this time it's a 0. We're going to be looking at this row again, right? We're going back to the A, right? The first three are visited already, right? So this one have been visited, so we're not even going to bother with them. This one hasn't been visited, and it is equal to 1. So now we're going to return J, right? That thing. So now we're returning the 3, right? V is equal to 3, right? We're going to do another push on the stack, right? We put the D in the stack in there, and so on and so on and so on.